In this session, we're going to see a process called Cramer's rule. And to kind of justify where it comes from, we're going to solve the system ax plus by equals e, cx plus dy equals f for x. We're going to do so by elimination. I'm going to multiply the first equation by d. I'm going to multiply the second equation by negative b. And of course, what I mean is multiplying both sides in both cases. And when I do this, my first equation becomes a dx plus b dy equals ed. And the second equation becomes negative bcx minus b dy equals negative bf. And if I add these two together, I eliminate the y terms. And I have a dx minus bcx is equal to ed minus bf. I know this is really weird, but just roll with it for now. I'm trying to solve for x, and I notice that I have x in two terms on the left-hand side. And so I'm going to factor the x out, and I'm left with ad minus bc. And on the right-hand side, I have ed minus bf. Dividing by the parenthetic quantity to isolate x, I get ed minus bf divided by ad minus bc. What did we just gain from this? Well, not a lot except for one thing. If we look at the coefficients a, b, c, and d, if we were to form a determinant with those letters, or those variables, a, b, c, and d, and then compute the determinant with the crisscross applesauce technique that we've seen, we'd have ad minus bc. That ad minus bc is showing up in the denominator of our value of x. Now that's interesting, but this next thing is really cool. If I take the constants e and f and replace the first column that had the x's coefficients, then I would have the determinant eb fd. And if I computed that determinant, again using crisscross applesauce, I'd end up with ed minus bf. That is showing up in the numerator of our expression for x. What this gives us is a way of solving for x. Folks, we could solve for y using determinants as well. What we would do is, instead of replacing the x column like we did, we would replace the y column with ef. The x column would remain ac, and we'd have this new determinant af minus ce, and that is what would go in place of the numerator for y. This process is called Cramer's rule. Yeah, I was teaching this one time. The student raises his hand and says, "Who came up with this?" I'm like, Cramer. Let's see how to do this. Our instructions are going to be solve the system using determinants if possible, or you might see solve the system using Cramer's rule if possible. Our system is 6x plus 12y equals 33, and 4x plus 7y equals 20. That first equation, 6x plus 12y equals 33, is divisible by 3 all over the place. And I don't know why I'm up talking right now, but I'm going to divide both sides of that equation by 3. My system is now 2x plus 4y equals 11, 4x plus 7y equals 20. So you get to do that. You could divide both sides of an equation by a number, right? Now, here's what we're going to do. We're going to form a determinant of coefficients. So 2, 4, 4, 7. And then we're going to form another determinant, but we're going to replace the x column by the constants. And so 11, 4, 20, 7. And then we're going to do it again, but we're going to replace the y column. And so 2, 11, 4, 20. Now, it would be kind of easy to get lost in all of this, so what we're going to do is we're going to label stuff. The determinant that we got from just using the coefficients of the variables, we're going to call d. The determinant that we got from replacing the x column with the constants, we're going to call dx. And the determinant that we got from replacing the y column with the constants, we're going to call dy. Let's go ahead and compute these determinants. So pause the video and crank them all out. And I get that d evaluates to -2, dx to -3, and dy to -4. And now here's the deal. X is going to equal dx over d. Y is going to equal dy over d. And so in this case, we're going to have that x is equal to 3/2. And in this case, we're going to have that y is equal to 4/2, which is 2. Since this was a system, we should wrap it up like we do with systems. X comma y is equal to 3/2 comma 2. I encourage you to check these in the original equation. You will find out that through this beautiful process, we have found the solution. This is one of the more painless ways to solve a system. Here's the deal, though. Cramer's rule only works for linear systems. Here's another deal. It doesn't even work for all of them. See, we're forming fractions, dx over d and dy over d, and as you can maybe imagine, this would fail if d turns out to be 0, because we can't divide by 0. But as long as d isn't 0, we can do this all day long. Next, we have the 3x3 case. Solve the system using determinants, or Cramer's rule. Our system is x plus 2y equals 8, x minus 3y plus z equals -2, 2x minus y equals 1. The first thing we do is form our determinant d. D is going to be just the coefficient determinant. So 1, 2, 0, 1, -3, 1, 2, -1, 0. Then we're going to form dx, dy, and dz. Even though I haven't told you what dz is, I bet you know how to do it. We're going to take the constants, 8, -2, 1, and for dx, we're going to replace the first column with those constants. For dy, we're going to replace the second column that came from the coefficients of y with those constants. And for dz, we're going to replace the third column, which was the coefficients of z, with those constants. In each case, the other two columns stays the same as what we had with d. Now we have our determinants, d, dx, dy, and dz. And as before, x is going to be dx divided by d. Y is going to be dy divided by d. And z is going to be, can you guess, dz divided by d. It's really elegant, kind of cool. And for d, I notice we have a column that has 2 zeros in it. Oh my gosh, it's an embarrassment of riches. And so we're going to use our sign array and the minor of 1. We're going to cross out row and column containing 1, end up with a determinant 1, 2, 2, -1, and figure out what this is. So this is going to be -1 times -1 minus 4. Seems to me the answer there is 5. What I'd like for you to do is go ahead and compute dx, dy, dz, and find x, y, and z. So what I did is I expanded down the third column of dx. I did likewise for dy. And then for dz, I used the shortcut where we reproduced the first two columns because there weren't any zeros to take advantage of. And let's face it, it's a quicker way to go through a 3x3. Remember, you can't do that in the 4x4 case. You just have to expand by minors. Ultimately, though, I end up with dx is equal to 10, dy is equal to 15, and dz is equal to 25. So, in this case, we're going to have that x is equal to, since it's dx over d, we have 10 over 5, or 2. Y is equal to dy over d, or 15 over 5, and so 3. And z is equal to dz over d, and so 25 over 5, which is 5. We're of course going to tidy this up and say that x, y, z is equal to 2, 3, 5. You're encouraged to check our answers in the original system. I'm moving on to our next example. Same instructions. Solve using determinants or Cramer's rule if possible. Our system is x plus y plus z equals 4. Negative 2x minus y plus 3z equals 1. Y plus 5z equals 9. I'm first going to compute d, which is 1, 1, 1, negative 2, negative 1, 3, and 0, 1, 5. I'm going to do this, I'm going to expand down the first column. That's what I'm going to do. And so I have coefficients of 1, negative 2, and 0. And then according to the sign array, the 1 has a positive cofactor. The negative 2 has a negative cofactor, so it's negative, negative 2. The 0 has a positive. We don't care about that because we aren't going to do anything with it because it's 0. And then we have our minors. The minor of 1 is going to be negative 1, 3, 1, 5. The minor of negative 2 is going to be 1, 1, 1, 5. And the minor of 0 doesn't matter, but I'm still going to write it. 1, 1, negative 1, 3. Of course, that's 0, so we're not going to look at that one anymore. And then I'm going to go ahead and bring this home. And I get that d is 0. What this means is Cramer's rule isn't going to work. What it further means is our system is either dependent or inconsistent. The way we would figure it out is it's going to be dependent if d, dx, dy, and dz all equal 0. If d is 0, but any of dx, dy, and dz are not 0, then it'll be inconsistent. I don't really feel like doing all that just to figure out which it is. I'm actually going to just go ahead and let's solve the system using another technique. Hey, how about an augmented matrix? 1, 1, 1, 4, negative 2, negative 1, 3, 1, and 0, 1, 5, 9. Right now you're thinking, hey, you're supposed to use Cramer's rule. Yeah, it also said if possible. And if d is 0, it's not possible. So I'm not going to bother. And I already have a 0 in the lower left corner. I'm going to show you how we're going to do this kind of in a short kind of bailout type of way. I've got to start off the way we know how to do it, which means what I'm going to do is replace row 2 by 2 times row 1 plus row 2. When I do that, row 2 becomes 0, 1, 5, 9, which as you can see matches row 3, 0, 1, 5, 9. As soon as I see those two that match, I know that I would end up with 0 equals 0. So this thing's dependent. What that means is now I bail out of the matrix, and I have the equation y plus 5z is equal to 9. which means that y is equal to negative 5z plus 9. In other words, I now have y in terms of z. So I want x in terms of z. I go to the first equation. X plus y plus z equals 4. No, I don't have it memorized. I used the first row of the augmented matrix. Because y is negative 5z plus 9, I'm going to make that substitution. I have x minus 5z plus 9 plus z is equal to 4. I'm going to collect like terms and isolate x. And when I do that, I have x is equal to 4z minus 5. And so x in terms of z. I will tidy this up using the set of ordered triples x, y, z such that x is equal to 4z minus 5, y is equal to negative 5z plus 9, and z belongs to the set of real numbers. Close that barn door, and here's our dependent system solution. Generally though, Cramer's rule, good way to go.